All right, Reagan, I've got something special just for you for this chapter. We're going to check this out, see what you think. All right, so we're in chapter 5, projectile motion, and here's the big idea. Projectile motion can be described by the horizontal and vertical components of motion. So we're going to break down motion into those components. In the last chapter, we studied motion in a straight line, and that was linear motion. And now what we're going to do is we're going to talk about if we throw a baseball or if we do something where we've got a combination of two different paths really put together. First of all, let's go back and review a little bit about vectors and scalar quantities. Remember, a vector is one that has magnitude and direction. So we're talking about vectors, magnitude, and direction. Scalars would only have magnitude, no direction in that example. Okay? So a vector or a quantity that's completely described by magnitude is a scalar quantity. So we can talk about like 3 kilograms of something, 3 kilograms of sand, or 1 kilogram of cement, and we add them together and we get 4 kilograms of total mixture, or 5 liters of water, and what do we got? Poured from a pail that has 8, we get the resulting volume is 3. Or it takes a 60-minute trip and you've got a 15-minute delay. The total trip time is 75 minutes. Notice that we didn't need anything else. We didn't need direction. We didn't need anything like that when we were talking about those particular things. So those are scalar quantities, and that's how they differ from vector quantities. Vectors would have a direction to go along with them. So let's talk specifically about velocity vectors. And we can take a couple of velocity vectors, put them together, and get a resultant. Remember, we talked about the parallelogram method, and we could put those together and we can figure out what they were. Well, you can do that. I mean, we can make it just very, very simple. Let's say, for instance, that we've got this vector right here. Okay? And we're going to use 3 centimeters, and every centimeter is going to be 20 kilometers per hour. So this vector represents 60 kilometers per hour, and it has a direction. In this case, we'll call it east. So that's what that vector represents in that case. Well, let's say that we're talking about this airplane. So Charlie, this one's for you. This is good, airplane vector velocity, good stuff here. And the airplane's velocity relative to the ground depends on its velocity in the air and the wind velocity. So, for instance, let's say that we've got this airplane, and this airplane, 80 kilometers per hour. But the wind going in the same direction, 20 kilometers per hour. Well, so what's his total? Well, pretty simple. Add them together, and you get 100. However, if he turns around and goes the other way, now he's going 80, but the wind is going against him at 20, and his resultant is only 60 kilometers when it's all said and done. All right, so the velocity of something is usually just combining 2 or more different ones together. So in this particular case, we combine those together to either got 100 or we got 60. Now, let's say this. Let's make this a little bit different. Let's say that we had an 80 kilometer per hour airplane flying north, and it's in a strong crosswind blowing from west to east. Well, what does that mean? What happens there? What are we going to get? So here's our airplane going 80. Oops, let's go back on that. Here's our airplane going 80 kilometers per hour north, but the wind 90 degrees to him, 60 kilometers. Well, remember, we did parallelogram idea. So we said, well, you could draw this parallelogram here, and this resultant vector right here, that would be what it really is. That's what the airplane is actually traveling at, and that's where it would be. And so, for instance, if we wanted to figure this out, and notice that they picked some pretty good numbers. So this is 60, this is 80. In other words, it's a version of the 3, 4, 5 triangle. So this would be 100 kilometers per hour. So this also results in the airplane going at 100 kilometers per hour, even though the wind didn't push it forward or didn't push it backwards, just pushed it to the side. Still, relative to the ground, this airplane was moving 100 kilometers per hour. Now, it wasn't relative to where it wanted to go. If this was where it was trying to get to, it ended up over here, he'd still have to go back this way. You know, in reality, what he's going to do is fly over here, get pushed over here, and end up there. But if we're just looking at it truly relative to the ground, he's still going 100 kilometers per hour. So here's just, you know, I think they're just showing you another example here. This is a 345. Anytime it's 345, it's going to be a 37-degree angle. Here's another common one. If they are both the same, you know, here we have one. We have one. Well, anytime we have that, you know, it's x and square root of 2 times x, whatever that is. So, you know, if it's 1 and 1, this one is square root of 1, or 1.414. And that's always on a 45-degree triangle. So that's a special triangle. When you have 45, 45, 90 triangles, you're going to have that particular type of relationship there. All right, so let's think about this. Suppose that an airplane normally flying at 80 kilometers per hour encounters wind at a right angle to its forward motion, a crosswind. Will the plane fly faster or slower than 80 kilometers per hour? Well, the answer is it's going to fly faster. It's going to blow it off course, okay? But it's going to increase the speed. All right, section 3, perpendicular components of a vector are independent of each other. So these are going to be independent. Often, and that's important too, because a lot of times what we want to do is we want to take a single vector and we want to break it down or resolve it into its component vectors. And so a lot of times you can take it and resolve it into components that are at 90 degrees. This is known as vector resolution when we do this. So here's what Nellie Newton or whatever, and she throws the ball like this. But, you know, if we don't know that, it's a lot easier probably to work at it as a horizontal velocity and a vertical velocity, and we can just break that down. Just, you know, it's kind of the reverse of what we were doing with the parallelogram idea. We're taking now my resultant or my hypotenuse, and we're breaking it down into the components. So here's the horizontal component, or we'll call it x. Here's the vertical component, which we would call y. So here's another example. Got my arrow here. Break it down. Y component, x component. You'll need to understand how to do that. That's going to be important when we try to figure out different things, especially when we're talking about projectile motion here.